let's see, last time we've been doing functions, and last time was 2-3, which was what? It's called analyzing graphs of functions. And I remember the assignment was to somewhere like in the 50s or something like that, wasn't it? Yeah. So I guess let's just do our usual. Let's open it up to questions on that. Yes? Okay. I was afraid you were going to stop there after the word any. Glad to hear it was just that one section. So, yeah, well, I have good news for you. All that is the kind of stuff we were doing before. When it says find the zeros, what they're saying to you is, where does this graph cross the x-axis? Which just means set it equal to 0 and solve. And solve. And if you look at that, that's the kind of thing we've been hacking around with previously, especially with quadratics. You have three choices. You can use factoring, you can use the quadratic formula, or you could use completing the square. So, for the most part, those are kind of old, those are review problems. But if you want, I'll do one. It doesn't look, I would at least make an attempt at factoring. And if that didn't work, yeah, I'd probably go to the quadratic. Let me just say this. I think students that go to the quadratic always are kind of missing out on an opportunity to save a lot of time sometimes. I mean, the quadratic is wonderful. It always works. The bad news is it's a fair amount of arithmetic. And you got to make sure you put your A, B's, and C's in the right place. And I've seen some students in a real super rush actually use the wrong formula, use the quadratic formula with some letters misplaced, and of course then they got it all goofed up. So I don't know. Let's just give a quick shot at factoring that one. So this is number 15. I guess probably would help if I turn the power on. Okay, we've got 2x squared minus 7x minus 30, and we want to know the zeros, so we want to know when is that thing 0 high. So set it equal to 0. Let's try to factor. Let's give it a shot. It's obviously going to be a 2x and an x. And for 30, we got a lot of choices. We could use what? 6 and 5. Would that do us any good? See, if we did 6 here and 5 here, that would give us 5 and 12. And 5 from 12 is 7. Now if I can get the signs right, bigger one's got to be negative, doesn't it? Plus 5x minus 12. Yeah, that'll work. Now all you got to do is set each factor equal to 0. You should get 2 answers. Do you want me to keep going?
No, I didn't.
Okay. So, I see that as good news. It's not a major issue. Yep.
Number
19. Another one of those. Okay. So take it, set it equal to 0. This one is nicely factorable. I simply factored an x out. And then set each of the two factors equal to 0. So when I do that with x, there's one of my answers. And then when I do it with this thing, I added 1 to both sides, multiplied both sides by 2. Don't forget, if you take a square root, you've got to take them both. So I came up with 3 answers. This is not surprising. This is a third degree equation, maximum number of answers, 3. I would check them, but another one? Liz?
On the ones towards the end where you were finding the relative minimally maximally function,
Yeah, 49, you were supposed to approximate it. So it doesn't really matter a whole lot on an approximation. I would say rounding would be okay. Or you could have, I would have been happy with your .999 thing also. Not real picky. Whenever they say approximate, because see, they wanted you to look at the graph and eyeball it. Sounds like you might have used your, what do they call it, the trace function, which is fine too. I don't have a problem with that. But the idea here is look at your graph and about what seems to be the high or the low. You know, what they were trying to do there, everybody, is they were trying to get you hooked into, all right, you've done it algebraically. Now, this is what it looks like pictorially. And so they want you to make sure you see it from both sides. Yes? Okay. Well, you know what the word minimum and maximum mean. The word relative is on there for this reason. You're going to have some functions that, for example, might look like this. Okay? This point right here is kind of what? An intermediate high point. It's not the highest point because you can see we're going to get higher over here. But for that part of the graph, it's a high. That's what we mean by a relative maximum. And this would be a relative minimum. Is it the lowest? Is it the minimum? No. We're going to be lower. But for that portion of the graph, it's a minimum. So the word relative means just for that neighborhood. Does that make any sense? Trey? Or you weren't raising your hand? You can put your hand up. Sorry about that. Yes.
I have a question at section 25 to 29.
Yes.
Yeah. Like, okay, we graph it. I don't know how to type.
How to do that? How to do the graphing?
And like, it asks us to find the zeros.
Yeah. Okay. Well, you know how to graph it? Are you talking about mechanically? How do I get?
No, like.
You know how to get the picture.
Yeah.
Okay. Well, when they say find the zeros, what they mean is now that you got the graph on there, about where is it cross the x-axis? That's what they're asking for. And so what they're saying is x equals what is where that thing bumps the x-axis. And if you want to use trace, okay, or really you can just eyeball the thing. And of course, if you have a parabola, you're going to get, and you, by the way, you may have to mess around with your zoom, right? You know how that goes. The previous zoom you had on your last graph might have been really far out, literally, and then you can't see enough, or it might have been way too far in, and you're whipping, the graph is crossing over there, and then you have to play around with the window thing. I'm assuming all of you know how to do that. Anyway, you may have to duke around with the window, but then you're supposed to see, oh yeah, about where does it cross the x-axis? Yeah. Other questions? 21. Let's see, what were they asking on that part? Find the zeros. Okay, let's, I don't know if I think I do. Okay, here's another cubic function. Notice they wanted to find the zeros, so I set it equal to 0. And then I did the old divide and conquer. I underlined my two parts. The first part I took a 4x squared out. The second part I took a -1 out, and I got very fortunate. A common binomial factor appeared. And so finally, it's not until this step here that I was actually able to factor it. But good news, I was able to factor it. Now, of course, well, I can even factor it further because isn't this the difference of two squares? And so I was able to do the 2x plus 1, 2x minus 1 conjugate thing here. So now I got three factors. Set each one equal to 0. Do a little algebra. Solve it for x. Not surprisingly, I got 3 solutions. Cubic. You know, you got to get a little bit lucky on those because, you know, after this step, if I hadn't had this x minus 6 in both places, I would have literally reached a dead end. And I don't know what I would have done. I would have had to maybe try to group them a little differently and divide and conquer a different way. I don't know. But at least it's your only shot, because we don't have a cubic equation memorized that we can use. So when you have something above a square, you really have no choice but to try to factor it somehow. Now, I will tell you this, where we're headed in this class, I'm going to show you some, well, you probably know them already, but I'm going to remind you of some extra powerful graphing techniques, so that, some extra powerful factoring techniques, so that you'll be able to factor a few more things than you thought you knew how to factor. It's called the remainder theorem. It's really cool. We're going to be heading there, I don't know, somewhere, I don't remember exactly where, but it's going to be in our course. I don't know, let's see, we can maybe do one more. Yes. 17? Okay, I took that fraction and I set it equal to 0 because they asked us to find the zeros. Well, the first thing I recognized is, if the top of this thing was 0, then that would make the fraction 0, wouldn't it? In other words, if x was 0, then this would be a 0, and this would be a what? A negative 4, and 0 over negative 4 is 0. So one solution that just kind of pops out at you here is this one. But of course, that's not the whole thing. I had to go on and do a little algebra too. So what I did is I took this and multiplied both sides by 9x squared minus 4. Well, that's this one. Yeah, okay, I see what I'm doing now. This tells me when my thing is undefined. So I also ask myself the question, when will the denominator be 0? Even though that doesn't tell me the zeros, it says, hey, when x is 2/3 and negative 2/3, this thing is probably got an asymptote. It's undefined. So, you know what we really need to do is look at the graph of this and just see.
Not a test, will you be specific if you want to know the zeros or when it's unkind or both? Or do you just want us to do both no matter what?
If it says find the zeros, that's really all I'm looking for. So this is really, I don't know, maybe not necessary, but I think a good student wants to think like that. Let me just quick do the graph and let's see what happens here. Okay, what was that? So we have a new function, and it's x divided by quantity 9x squared minus 4. Yeah. So I'll just zoom in on this a little bit more. So you see what's going on. When does this graph cross the x-axis? And the answer is only when x is 0. See, right there is where the graph crosses. What did the negative 2/3 and positive 2/3 tell me? It told me we had an asymptote there. So you see when we go over to 2/3, which is about here, you see how the graph approaches. So did that really tell me anything about zeros? No. But it told me a little bit more about the function. Do these ever get to 0? You can tell they get real close to it, but they don't ever quite get there. So x equals 0 is my only answer. So that extra part wasn't really part of the question, but I thought we'd throw it in there anyway. Does everybody see that? This graph only has one 0. Okay. Well, we better move on. I know if you probably, if you wished I spent the whole period doing questions, in a way I could. If you come and see me, I'll be happy to go through more. I just have this problem in class. I have to go on to some new stuff, even though there's tons of explorations we could continue to do. And if you want, we could maybe do some of that tonnage outside of class. All right, so here's where we're headed today. The book calls it a library of functions. And I think we've done a little bit of this already. What it's saying is there are some famous functions, maybe even things like the I don't give a rip function, more commonly known as the constant function. And what was another one I gave you in that one presentation that day? The lazy man's function. Wait a minute. The I don't give a rip was a constant. The lazy man's function was the identity function. It just kind of gives you back what you give it. Okay, but those are in our list today. But we're going to look at some others. You almost have to know some kind of famous functions so you have a beginning point. So what's the first objective here? Linear. Everybody knows how to do the mx plus b, guys. Squaring functions, good old quadratics. Here we have the cubic. The cubic generally has two humps, does something like this. Of course, the humps might be shorter, but it's that two-turn thing. Then we have the square root. That's just this guy turned on its side. And the reciprocal functions. And we'll be looking at all of those so you don't have to look up at my hand here. Number 3, the step function and other piecewise defined functions. Those are unique. In fact, you may not have seen much of those before the last week. And then finally, if I give you a graph, can you kind of look at it and go, aha, yes, that's the I don't give a rip function, or that's a quadratic. So that's kind of what we're going to do today. So this is the Mr. I don't give a rip, otherwise known as a constant function. It's just a good old horizontal line. It says I don't give a rip what you give me for x. You are getting, in this case, I don't know, what is it, about 1.2, 1.3, something like that? Or in a more generic form, you're going to get c. It's just a good old horizontal line. What's the slope of that line? 0. So in slope-intercept form, give me a more complete name for this in slope-intercept form. Y equals, what times x plus c? 0, right? Y equals 0x plus c. You don't, of course, 0x doesn't need to be there. That's why they didn't put it there. But okay. Then here's the lazy man's function. This says I'm just going to give you back whatever you give me. Remember, I made that crazy drawing that it was just a greased thing, and whatever went in on top just came flying out the bottom. That's basically what this one is. You give me a 2, you're getting a 2. You give me a negative 1.8, you're getting a negative 1.8. And so you have points like negative 1.8, negative 1.8, 2, 2, always the same y coordinate as x coordinate. Okay. And by the way, the identity function becomes really important later in the chapter when we do inverses. It's the what? Reflection line. Okay, then Mr. Quadratic, which we've been seeing so much of lately. This is the simplest one. Y equals x squared. They don't all sit right on the origin like that, but x squared looks like that. We've all seen that guy. Then the generic cubic function. Yep. Quadratic, what? I still think It's kind of an odd name because quad seems to imply 4 to me. But anyway, you know by now that a quadratic is a second degree equation. The third degree equation is, like I said, the one that kind of has 2 terms in it. Have I ever told you guys the turn rule? Okay, this is the TURN rule, and you won't find this in the book. This is strictly me, okay? Here's how it works. It says take whatever the degree of the equation is, in this case 3, and subtract 1, okay? 2. That's the maximum number of turns that the graph has. By that I mean if you're on this car, you got to turn right, and you got to turn the wheel to the left. 2 turns. Right turn, left turn. And even when the humps are bigger, you got to, if you're going like this, you got to make a right turn, now change it to a left turn. So it doesn't matter how big the humps are, that turn rule kind of works. If I gave you a 7th degree equation, it could have up to 6 turns in it. What if I give you a first degree equation, like y equals 2x plus 3, first degree? Okay, what's the degree? 1. Subtract 1, 0. What's the maximum number of turns? 0, because it's straight. The turn rule is kind of a handy little thing, so that when you are handed an equation and told to graph it, you already really, by the way, that's the maximum number of turns. It could be less, right? So if I gave you a 4th degree equation, it could have up to 3 turns, but it might have less. So, I don't know. At least you know it doesn't have more than that. Then there's the square root function. This is only the positive square root. And I'll tell you why. If I put both plus and minus on here, it would look like what? Let me change colors here. Then wouldn't it look something like this? I mean, the other half would be the reflection down below. And then they couldn't use the word function, because then wouldn't it fail the vertical line test? So that's the only deal there. So what's the square root function? It's just, half. And so it really is a function. It's just like the plus root or the minus root. That's really just half of a parabola. Okay. The reciprocal function, this is pretty famous. By the way, it's sometimes called a rectangular hyperbola, because you guys remember from high school geometry what a hyperbola is? It's got those 2 branches. Well, if you take, normally it looks like this, but if you just take it and tilt it 45 degrees, it looks like that. Anyway, what's going on here is this is asymptote heaven, because this thing never crosses the x. This thing doesn't cross either the x or the y-axis, but it's forever approaching them in 4 directions. So x can't be 0, real obviously. You can see that in the equation. It would create trash. And why can the answer never be 0? Well, the only way a fraction can turn out to 0 is if the top is 0, and the top is clearly not 0. So it's never going to happen. Y is never going to be 0. Sure enough, we're never going to cross the x-axis. Okay? Now, if you haven't seen this one, we're going to be trying to get familiar with this today. This is called the greatest integer function. And it's like a little stepladder. Very similar to the kind of thing you see when you actually do a rounding off function. By the way, they have this double bracket symbol down below. F of x equals bracket, bracket, x, bracket, bracket. I usually have, most of the books I've seen it in, it's single bracket. So if you ever see square brackets around x, just a single pair, that usually means the greatest integer function. Now let me tell you what it is. Here's how it works. It says, whatever you give me, I'm going to give you back the greatest integer less than or equal to the number you gave me. So, for example, if I give it a 2, what's the biggest integer that's less than or equal to 2? And the answer is 2. Okay, how about 2.2? What's the biggest integer less than or equal to 2? 2. How about 2.8? 2. How about 2.9? 2. How about 2.9999? 2. So do you see what? We're in all these 2.1, 2.2, 2.3. Do you see how they all come out same height, 2? But as soon as I go to 3, it vacates and hops up. Because the greatest integer of 3 is 3. What's the greatest integer of 3.2? 3. 3.4? 3. But as soon as I go to 4, then it would hop up. Okay. Now, be careful on the negative stuff. Watch this. You know, it's tempting to think, oh, this is easy. This is called ignore the decimal. And you know, it actually is in positives. You know, if we take the greatest integer of 2.111, it basically is just ignore the decimal. But I shouldn't have told you that because it doesn't work with negatives. Because when I take the negative integer, the greatest integer of negative 2.1, think about this. What's the greatest integer that's less than or equal to negative 2.1? 3. That's right. So you see how I can't just drop the decimal, and sure enough, look up here. If you go over to negative 2.1, sure enough, we're down here in the negative 3 bar, just like you said. Okay, now why is it always solid on the left and open on the right? Because as soon as you get to the next integer, it's always going to hop up. And that's going to be the beginning point. So please note that these little stairs always have a solid dot on the left and an open dot on the right. Is this a function? How could you convince me that this is a function? Yeah, the vertical line test, exactly. Because when I do a vertical line test, and of course here is pretty obvious we're fine, it's only crossing in one point. But when I come here, it's still only crossing in one point. It's crossing here, and this is, remember, naked right here. So I'm okay down there. I don't have a double crossing. So this fits the definition of a function. Okay, that's, how many of you have seen that before? Okay, it's actually, there's a lot of things in life that work like this. One I always talk about with students is a parking lot function. Let me explain. If you ever go to a downtown area of a city where they have, you know, a multi-floor parking facility, they always have to have some rule for how they charge you for parking, right? And the rules usually go something like this. I probably have the numbers wrong, but it doesn't matter. It's the same principle. What they usually say is, for the first half hour, I don't know, it's $2. And then, for every half hour you add on to that, it's another 50 cents, let's just say. So the meaning is, for anything between 0 and 30 minutes, I owe them $2. So if I drive in there and go, oh, I forgot my wife, and I drive out, I owe them $2. They don't give a rip if I'm only been there for 10 seconds. Any amount between 0 and a half hour, I owe them $2. Well, guess what? That looks like this, except this would be up here at $2. So there'd be a little horizontal. I don't know. It's the same kind of deal. And then, if I stay there for 31 minutes, I owe them $2.50, because the rule says any amount over 2 hours, you're going to have to bump up 50 cents for half, you know. And so you're going to get all these little horizontal bars, just like this. So this kind of thing is done. This is very common. It's actually very lifelike. If you thought it was strange, actually, this is what rounding off looks like too. You know, when you get to 0.5, well, then jump up. It's the same kind of a concept. Okay. All right. Yeah, here's some of the stuff like I did on the board. I guess I did use the double bracket here, like the book does. You know, what's the greatest integer of 2? 2. What's the greatest integer of 2.1? 2. What's the greatest integer of 2.9? 2. Might as well take a nap, right? Keep getting 2. Of course, until I do go to just a hair over 3, now I'm going to be stuck on 3 for a while, and so forth. And be careful of the negatives. Remember, what's the greatest integer of a negative 2.9? The greatest integer that's below is a negative 3. So you can't just do this dropping of the decimal thing. Okay, now let's go to the book. Let's see what we got for assigned problems, and let's. By the way, the library is shown in your book on page 215. They pretty much got them all there, all the same ones. So if you were having trouble getting some of that down from up on the board there on the screen, it's the same thing as there. Oh, I do want to show you a piecewise function. Okay, let's do that next. Let me make one up. So here we go. A piecewise function just literally means a function defined in more than one piece, or chunk. You could call it a hunk function because it's just a bunch of different pieces. So for example, we might have one defined like this. Right away, it's a tip-off that when they give you a function that has like a bracket after it, that's a tip-off that, oh, this has got more than one piece. And so they might write it like this. They might say, all right, we're going to have this function be x when x is greater than or equal to 0. But we're going to have it be negative 2 when x is to the left of 0. Okay, so I've literally defined for you two separate pieces. Let's take a quick look at what this looks like. Okay, so now if we do our graph in blue, how does this look? It says, all right, whenever you're on 0 or to the right of it, then the answer is just it's just x. And so that basically says we got this point and, you know, a straight line that forever goes that way, right? That's the good old, that's the lazy man's function, but only from 0 to the right. But when you're to the left of 0, then you're stuck at negative 2. That's supposed to be a horizontal line. And you notice I made this an empty point here because this says only when x is to the left of 0. So it's just saying, all right, this is like I guess I'm back to schizophrenic again. This is actually a schizograph because it's like it's got two identities. Whenever it's to the left of 0, then it's a horizontal line down here at negative 2. Whenever it's 0 or bigger, it makes believe it's the identity function. And is it a function? Yeah, it passes the vertical line test. Now, if this was filled in, it would not be a function. So if there was an equal sign here, then we would have a problem. But you're not going to have that conflict come up. I'm just saying. Okay, so this is a piecewise function. You know, it might be a straight line on one side and then half of a parabola on the other side. It could be any. It's kind of like this is like algebra Legos. Okay, you're like, oh, I think I'll take some of that graph and put it over here, and I think I'll take some of that graph and put it over here, and then oh, I got a really good one for the third piece. Let's do this. You can do that and make a piecewise function. And so you could actually, for example, draw out the letters of the alphabet. using pieces of things. You put them together cleverly. That's not what we're going to do, but you could. Okay. Well, with that, by the way, there's a look at the piecewise function at the top of page 215 in your books, please. You see way up on top of 215, they have, don't look at the graph, but, well, you can look at both. Right to the right of it is the piecewise function. Notice it's defined with two pieces. It says, when x is less than or equal to 1, then I want you to use the equation 2x plus 3. Okay? And when x is greater than 1, then use this equation. Notice when it's less than or equal to 1, it's got a positive slope. And when it's greater than 1, it's got a negative slope. And that's why you notice the two bars that are in different directions. So how many of you have done piecewise functions before? Just kind of half and half. Okay. I mean, as you can tell, they're really nothing special. They're just kind of graphs that are welded together. Okay, now let's look at the assignment in the book. On the first 8 problems, it says, write the linear function that has the indicated function values, then sketch the graph. Okay, so first of all, they're telling you flat out, this is a line. That's important. Notice it's a linear function. So they're telling you it's a line. So what kind of an equation must those problems have? Mx plus b. And then, what is this f of 1 equals 4 stuff and f of 0 equals 6? How can I use that to find the equation? Those are really ordered pairs. Yeah, they really just gave you 1 comma 4 and 0 comma 6. So how do you get an equation from that? Remember, find the slope. Once you know the slope, plug it in for m. This one is, number 1 is extra nice because of what? Anybody see something about that would make it just a little bit easier to finish up? Keep looking. You should be able to see this. What's that? Yeah, okay, I'll accept that. The numbers are positive, therefore a little easier to calculate with. Yep. Yeah, what is the y-intercept? Yeah, they gave you the 0.06, so they handed you mx plus b. They handed you b on a silver platter. So, whenever you get one of those, just do a little silent thank you. And then make use of it. Save yourself a little time. Okay, let's go to 9 through 28. Go ahead and do these on a graphing utility. And it says, notice they say be sure to use an appropriate viewing window. In other words, if you hit the graph button and you don't see anything, you don't have an appropriate viewing window, okay? Let's face it, if you use a graphing utility, that can happen, right? You graph it and you go, what's wrong with this thing? And they want to kick it, give it a knock, it's not working. Actually it is, but you're looking at a window where it isn't. And so half the problem is changing the window. By the way, have any of you downloaded Graph? It wouldn't work. Oh, you mean you couldn't find it? Oh, that's different. Were you able to find it? Okay. I've never had, it was the first thing that comes up when I do Google. It shouldn't be, I didn't make it a hard one to find. I don't know. Did you use Google? Why don't you just put this in next time? Put the word graph in, and then space, I don't know, graphing utility or something like that? Or software, or download?
Download graph.
Download graph. There we go. And it was the first one?
Yep.
Yeah. And were you able to make use of it? It's now, I'm pretty sure it only works on a PC. I don't think I'm not sure if they have a Mac version of that. But anyway, okay. By the way, I have a graph here. You know, one thing I like about graph is if you want to change the window, just grab the hand. If you want to just move it around, and you can just literally grab the graph and move it around, that's a lot more intuitive than doing this window thing. And then if you want to zoom in, just hit the plus key and zoom out. And so you can do all kinds of cool window things without having to do that window stuff, you know, because then you got to go, all right, window, I got to move down left. So okay, and it takes a little while just to figure it out. Anyway, okay. You know, besides just doing things on your calculator, I hope when you do a problem like 27, you're going, you know something? X can't be negative 2. So what probably is going to happen when I do a graph? There's probably going to be an asymptote at x equals negative 2. By the way, some graphing utilities don't get asymptotes very well. Something I like about graph is it gets asymptotes. On a calculator, it'll usually just try to connect them. Like if you do y equals 1 over x, it's supposed to look like this. Okay? A lot of graphing calculators will do this, and then it'll go, I better connect those. And for the person who doesn't think at all and just goes, oh, my calculator's got to be right, they'll think that's supposed to be in there, and it's not. And here's a case where if you look at 27, you go, x can't be negative 2. There's no way there could be anything at negative 2, and if my calculator shows it, I hate it, or whatever utility you're using, it can't be right. So, careful. Some graphing utilities do guessing like that. And I hate to tell you this, but they sometimes guess wrong. And you got to have enough algebra moxie to go, hey, I know better than my calculator. Okay, yes? No, you don't have to, no. So, if I collected, you don't have to have that down. But I really need you to experience it, okay? So whichever way you're going to do it, software or using your calculator. And I don't expect you to get a printer. There are ways of printing from a calculator too. You don't have to mess with that. Okay, 29 to 36 says evaluate the function for the indicated values. So mostly I want to know, do you get the notation here? Do you get what they're asking you to do in 29a? Well, before you know what to do in 29a, you got to look at the function. What is the function in 29? What does that thing mean again? We call it the greatest integer of x. So what are they asking you to do in 29a? They're saying, what is the greatest integer of 2.1? What's the biggest integer less than or equal to 2.1? 2. Okay, so a is 2. B, what's the greatest integer of 2.9? So do you get the notation now? Okay. How would I do C? I would probably find somebody smart and say, give me the answer or you die. No. What's the greatest integer? I would be happy to do that. What's the greatest integer less than or equal to negative 3.1? Negative 4, because, see, negative 3 is above it. So I can't use that. I got to use something below. Okay, or on or below. What's going on in a problem like 36? It says, now you guys got to look at this function, 36. It says g of x equals negative 7 times the greatest integer of x plus 4 plus 6. So whatever number I give you for x, like let's just quickly do a, you plug in 1/8. What is 1/8 plus 4? 4 and 1/8. Now, what's the greatest integer of 4 and 1/8? 4. And now what's 4 times negative 7? Negative 28. And what's negative 28 plus 6? Negative 22. So it's just got to use that new operation called greatest integer. And they got some graphs for you to do. That we want you to do manually. By the way, I don't think your calculator is... I don't even remember about graph. You're going to have to do that one on paper. I mean, that section on paper. You're going to have a bunch of little step ladder-like things. But they're not all going to be... The steps won't be in exactly the same place, right? You know, what's going to be different about number 37, for example, from the one I gave you in class? How is number 37 going to be different from that? Well, instead of going uphill to the right with a positive slope, isn't it going to be going downhill? Yeah. And you got to make sure you got your solid dots on the right end and all that kind of stuff. Be careful. All right. 1 through 71, the odds. 1 to 71, the odds. Have a nice weekend. See ya.